second, the sun's core produces enough energy to fuel our world for 1 million years. If we could create our own sun here on Earth, we'd have a source of energy that's safe, clean, and endless, without the risk of meltdowns or radioactive waste. That process is called fusion.
If fusion were possible, I think it would ease the suffering of many people. It would allow many more people to be prosperous. It would allow the environment to be cleaner. Fusion is the holy grail.
Like the quest for the Grail itself, the path to fusion is an epic journey. But this Grail actually lies within our grasp. In a world running out of fuel, the world's best engineers are figuring out how to power our cities using some ingenious methods. Solar, wind, steam, and in this episode, nuclear fusion. In this lab, scientists are playing God, trying to create another sun.
Yeah, it's a passion that's just taken hold of me. I can't explain why. It's just the thought of recreating a star in the laboratory excites me. It occupies my work life, and at night I have ideas on how to do it better.
Good thing John stays awake thinking about power, because our planet is guzzling energy. In 40 years, the world's population should grow by 50% to reach 9 billion people. But energy demand will triple as the third world industrializes. More people will compete for the same amount of water, and the shortage will require huge desalination plants, consuming even more power.
We have to do something different. We know that. We know consumption in Western countries is much higher than it is in the developing world, by factors of 100 in some cases.
Today, 80% of our energy comes from fossil fuels, and they're running out. Before they do, they'll fuel global warming. The next generation will need fuels that are clean and abundant. But renewable energy alone costs too much and does too little. Replacing one power plant would require 60 square miles of solar panels, or 2,500 giant wind turbines. Without a viable source of energy, we're heading toward catastrophe.
Nuclear fusion is part of the answer as well. It's something that's clean, it's safe, it's something that's got essentially a unlimited fuel source, so we think it's got to be part of the long-term answer.
If scientists succeed, we'll have a source of power that's heaven-sent, safe, clean, and abundant.
Fusion is, after all, the, if you will, God's economy of scale for powering the universe. It's the way stars work.
To grasp what they're doing, you have to step back 14 billion years. Little by little, gravity captured the hydrogen in the early universe and gathered it into clouds, then stars. The immense pressure in the heart of a star crushes hydrogen atoms against each other. They heat up and merge to form helium in a process called fusion. In the core of our sun, fusion has been happening for 4 billion years. Every second, 600 million tons of hydrogen are turned into helium, enough to power the whole Earth for 1 million years. To create their own sun in the laboratory, scientists will use machines out of science fiction. Access to these sites is a real privilege, and their world makes your head spin. Here, numbers never have fewer than 6 figures. To top it off, there's more than one way to achieve fusion. So which way is the best? Around the world, teams of scientists are competing in a fusion marathon. First contender, the Z machine, which uses powerful electrical pulses to ignite a fusion reaction.
The facility was built to create these extreme states of matter for nuclear weapons research, but now we're doing a lot of experiments to create fusion in the laboratory. That is, a miniature star in the lab.
Second team, the laser megajoule, whose beams will smash hydrogen like hammers until it explodes.
The fuel for fusion will come from seawater, which is an almost inexhaustible source.
And last but not least, ITER, a futuristic boiler that will house a continuous fusion combustion within a magnetic cage shaped like a ring.
The amount of energy involved is like millions of times more than what you get on a conventional chemical reactions.
Who will be the first to harness the energy of nuclear fusion? The winner will be the team that develops a fusion technology that produces more energy than it uses, the key to a working reactor. One team begins by building its own lab in the south of France. And they start with a bang. An entire hill is leveled to make room for ITER, the next generation of experimental reactor.
So this is the ITER site, and this is where the ITER fusion reactor is going to be located.
ITER will be a lab for scientists to perfect fusion. If they succeed, they'll design a prototype reactor to produce electricity. The budget is as huge as the site, $17 billion. Governments representing half the population of the world are collaborating. The European Union, the US, Russia, China, India, Japan, and South Korea. Each partner will construct a certain number of parts manufactured by their top high-tech companies. Once the site is complete, scientists from all over the world will converge here to reach their goal. To produce 10 times more energy than is consumed by the reactor for at least 6 minutes. 6 minutes is long enough to prove the technology will work. The reactor chamber will be 10 times bigger than any experimental fusion device yet built. ITER means the way in Latin. If it succeeds, it will pave the way for a full-scale fusion reactor and make today's nuclear plants the plants of the past. Nuclear energy literally means the energy of nuclei. Today's nuclear plants generate power using a process called fission. Fission breaks up the unstable nucleus of large uranium atoms. The energy release spins turbines that generate electricity. But fission has its hazards. More than 2 decades after the accident at the Chernobyl nuclear plant, people continue to die, and we still have no long-term solution to nuclear waste. Fusion is the opposite of fission, and by its very nature, fusion is safe and clean.
You know, the fusion reaction is one that involves 2 light nuclei, putting them together, fusing them together to form a heavier nucleus. And in the process, according to Einstein's equation, E = mc², a large amount of energy is given off.
1 gram of fusion fuel equals the energy of 8 tons of gasoline, enough power for an average car to drive around the world 3 times. But there's a catch. Fusion occurs only at high temperatures, very high. At 200 million degrees Fahrenheit, the matter is heated to the state of plasma, 10 times hotter than the sun, hot enough to overcome the nuclei's natural repulsion and for the atoms to fuse. The ideal atoms come from 2 kinds of hydrogen, deuterium and tritium. Deuterium is endless. It's found in seawater. Tritium comes from lithium, a metal found in the Earth's crust and the oceans. And we have enough to last for hundreds of thousands of years.
The fuel is very available. You know, the analogy we like to talk about, the comparison is, if you take the deuterium in a bathtub full of water and combine with that the lithium in a laptop computer battery, there's enough energy there to provide the energy needs for an average person for 30 years. It's phenomenal. It's very safe. You know, we have a plasma that's contained in a magnetic field, and if this plasma gets just a little off of ideal conditions, the process stops. So having some unsafe runaway condition is impossible.
The fusion reaction itself doesn't produce dangerous waste, but the neutrons bombarding off the chamber wall will make it slightly radioactive. Tritium used in the reactor has a 13-year half-life. After 20 to 30 years of operation, ITER will be dismantled. Within a century or so, most of the radioactive parts will be too weak to pose a threat.
ITER has these high sides: clean, safe, available fuel, essentially unlimited fuel source. So that's the reason I'm here. It's the reason I've got 300 colleagues in the office building a kilometer behind you, all working to make this happen.
Next to the construction site for ITER is the Tor Super Tokamak, ITER's forerunner. What happens here will happen inside ITER, but on a much bigger scale. Tokamak is shorthand for a Russian phrase meaning toroidal chamber with magnetic coils.
That allows us to get up to temperatures of 200 million degrees Fahrenheit. That's what we need to reach the conditions for fusion.
As in all tokamaks in the world, the Tor Super Team spends a lot of time taking apart, evaluating, and improving the parts. Fusion requires perfection. Today, the team is replacing a microwave heating antenna, a crucial part for reaching high temperatures. Philippe is the machine's operator.
The design for ITER is not completely locked down. We're in the middle of installing a hybrid heating antenna which will allow ITER new options for heating the plasma and for lengthening the time of the discharge.
Serge has been using the machine for over 20 years. He witnessed its construction and knows every detail. To supervise this delicate move, he has rehearsed with his team all morning.
You're bumping against the slides, see?
In a Tokamak, all the space is completely used up. If there was an empty spot, we would have installed something, a measuring system or anything. Anyway, there is very little space to install the systems. It all fits in by millimeters.
6 tons, 6 meters long, bristling with metal parts. Each piece is custom-made and the result of years of research. One misstep could leave a very expensive scratch.
It's okay. It's okay. I am centered in the pipes below.
Yes!
Stop!
I'm no longer hanging on to it.
You
can't see. He's seeing less and less. We should turn the back, but which way?
Don't tell me what to do. Tell me where it's touching.
I'm telling you, Etienne, it's too low to push it in the ball joints. A supporting part needs to be re-machined a bit. We'll lose 2 hours. It's part of the risks with systems as complex as this one. To fit in each part, every millimeter counts. When we have a problem, we'll re-machine the part in the workshop before reinstalling it.
They modified the part that guides the antenna by shaving a few slivers of metal. These everyday problems are a part of the quest for fusion. Add up all the problems, and you have months of setbacks.
Let's try it like that.
There, it's going on its own, see?
Great, it's going in great.
Everyone can breathe now. But some jobs are beyond this team. Radiation, extreme vacuums, and high temperatures make a tokamak impossible to enter once it's running. To maintain this chamber will take a robot. This robot can sneak its 10 meters of titanium and steel through a shutter only 25 centimeters wide. In a few hours, it can inspect the walls and even fix small problems. And the experiments can continue without losing precious time. Another day at Tor Supra, and another experiment on the road to fusion. Today, testing the new hybrid antenna, a key to starting a fusion reaction. This kind of antenna could be ideal for ITER. To start the experiment, they have to turn on the tokamak, but they don't just flip a switch.
Every morning, we put it in service, and in the evening, we put it on security settings so that people can enter the hall.
Each circuit breaker gives access to a key to open the next breaker. It takes a while, but you can't play around with 63,000 volts.
Anika, can we proceed?
No, we can't. A safety door won't close, so the tokamak can't start.
The plasma emits ionizing radiation. For safety reasons, no one can remain in the experiment hall. Otherwise, they would suffer a serious sunburn and could receive a fatal dose of radiation. We take safety seriously here. First step, we make sure the heavy door functions. All the Tokamaks subsystems are used to their limits, so it's no surprise to see small defects appearing once in a while. And we have to make repairs quickly so we can continue the experiments. This is something we won't be able to do once we have the reactor. We don't want to stop the reactor to repair the system.
The company that maintains the doors won't be able to repair it for several hours, so the staff scrambles to find a solution. Each day has the potential for a few hours of delay, which together could add years to the timetable.
So, what are they doing?
They've gone down into the bowels of the lab to track the bug along miles of electrical wiring. Seems a sensor thought the door was closed, so it wouldn't budge. Turns out the jammed door works fine. It just needed a nudge. The main door closes with no trouble. The team can now work safely, protected by concrete walls 2 feet thick.
Good. Good. Heavy doors okay?
Think of plasma as a very hot soup of atoms. Nuclei, positively charged, and electrons, negatively charged. Scientists will reconfigure the cooking methods thousands of ways before finding the ideal recipe. First, they switch on the magnetic field to maintain the plasma at the center of the vacuum chamber. A tiny puff of deuterium and tritium mix is injected in the experiment chamber. The central coil of the tokamak is activated. It heats the fuel by resistance like a toaster. The fuel is heated to the stage of plasma. No physical container could retain this hot plasma of atoms, so the scientists had the ingenious idea of confining it within a magnetic cage, hence the name, magnetic confinement. In a vacuum, the plasma is now protected from any substance that could cool it down and snuff it out.
Voilà. Good. We have everything. Data, all of it. Great. One run. One plasma run on the entire program of the day. So let's use the hybrid antenna.
Now they can start another experiment and test the antenna. Beyond 20 million degrees, this method runs out of steam. They have to raise the temperature by using another tool. Antennas now emit microwaves, the equivalent of tens of thousands of microwave ovens to heat the plasma. The hybrid microwave antenna directs heat at precise areas in the plasma, but it's still not enough. Reaching fusion requires even more heat. Deuterium atoms are fired at 700 millions of miles per hour, causing collisions that heat the plasma.
Take a look at the hybrid. Very, very good.
An infrared camera lets the team watch to make sure no parts on the wall of the chamber overheats. Today's machines can create only sparse fusion reactions. To make it work, we need a reactor 10 times bigger, thus the need for ITER. Within 2 decades, scientists at ITER hope to perfect the recipe for fusion and produce more energy than is consumed. Then, they can build the first industrial fusion reactor that can actually produce electricity. Heat emitted by the reactor will produce steam, and steam turbines will generate electricity. With the prospect of ITER, progress on magnetic confinement fusion has accelerated. But elsewhere, other teams are pursuing fusion with other methods, including the world's biggest lasers. Amid the vineyards of Bordeaux, French military research plays a key role in the race for fusion. Banned since 1996, nuclear testing has been replaced by computer simulation for developing new generations of nuclear warheads.
Let's go!
Weapons engineering and energy production share the same field of research, fusion. A national laboratory working for the military will open its high-intensity laser, the laser megajoule, to civilian researchers. Here, a team of physicists is working on a completely different method to achieve fusion: inertial confinement. No magnets needed to confine the reaction. It happens so fast that the nuclei fuse before they can scatter. A vast array of lasers will compress a mix of deuterium and tritium enclosed in a tiny capsule until they superheat and fuse together. Francois Jouquier supervises the installation of the experiment hall.
You're now in the target area of the laser megajoule. At the center is a room that measures 30 feet in diameter. In this chamber, 240 laser beams will converge towards a tiny target. The experiments in this chamber are aimed at achieving thermonuclear combustion. This is the first step to achieve what is known as inertial fusion energy, producing electricity from an inexhaustible source, namely seawater. Inertial fusion energy is the ultimate field that will enable us to provide electricity from fusion.
To shelter the laser array and its scientific equipment requires a building that would cover 9 football fields. The building is strengthened by beehive structures with enough concrete to fill 45 Olympic swimming pools. The temperature can't vary by more than 1 degree Fahrenheit to avoid deformities caused by the equipment expanding. And in the middle of that huge building, work happens on a microscopic scale. Accuracy is paramount. To be perfectly targeted by the lasers, the fuel capsule must be precisely positioned within 50 microns, the thickness of a human hair. Along a 100-kilometer optical fiber network, the command computer will have to control 2,000 video cameras and 10,000 motion controllers and synchronize 9,000 elements, some at 1/100th of a billionth of a second.
After working several months, even years, seeing the first steps achieved, well, it's a milestone in my physicist's career.
The laser requires certain lenses made of synthetic crystal, which engineers must grow themselves. In 2 months, they've obtained crystals measuring 2 feet across. So success depends on scientists as well as janitors. From construction to operation, everything must be spotless. 1 speck of dust can damage the laser equipment. After a thorough cleaning, this part is about to be installed in the laser bay. Like everything that enters the laser megajoule, it's moved into an airtight trailer.
Hey, backwards. 1 meter. Stop.
The thousands of parts for the laser megajoule will all go through this procedure. While some parts of the building are pressurized to repel dust, the experiment hall is depressurized to contain any tritium leaks. The air filtering system is as powerful as the turbines of a Boeing 787 Dreamliner. It takes up 1/3 of the whole building. Like ITER, the laser megajoule has its own forerunner, a less powerful prototype, and it's right next door. Equipped with only 4 laser beams, it can't produce a fusion reaction. Its purpose is to prepare the teams to simultaneously control the 240 lasers of the megajoule. The maintenance team must regularly inspect the lenses used most often. Despite the clinical cleanliness of the lab, microscopic dust sneaks onto the lenses.
Dust spreads on the lenses and is burnt by the laser. This damages the lenses. Given the cost of these lenses, it's obvious we try to avoid dust as much as possible. That's why we have these different clean rooms. Here, the lenses removed from a laser amplifier are brought to a clean room to be overhauled.
Ready to lift.
The clean chain has not been broken. The amplifier was extremely clean. We went through a cart, which is also very clean. And finally, we go into a room that is as clean as the plates cassette itself. There, it will be cleaned and reconditioned.
Ultraviolet light helps them detect and remove dust. Experiments go on by the thousands. Today, an alignment shot to perfect the laser's accuracy.
Securing room D5 and D9 to prepare shot.
It takes a whole team 3 hours to wrangle the 350 motion controllers that adjust the alignment of the lasers. If the temperature varies by 1 degree Fahrenheit or someone walks near the lasers, the beams will fail to reach their target.
We're finalizing the alignment. We'll start the shot in 15 minutes.
The shot begins with a tiny infrared laser, like the kind in a CD player, but which will be amplified 8 billion times. The laser passes through amplifiers. Strong flashes illuminate laser plates, which in turn transfer their energy to the laser beam passing through. The beam makes 2 return journeys, collecting more energy on each pass.
Evacuation of the switchyard target area to prepare for the shot sequence.
Évacuation de la zone 10 000 joules d'expérience pour préparation à la séquence de tir.
Are you all ready for the shot?
Yes. Yes. Okay.
Yes.
Experiment subsystems ready. High voltage.
Okay. Yes. Fine.
Synchronizing.
Ready.
Diagnostics.
Okay.
Alignment.
Okay.
Computers.
Yes.
Communication du PCI, lancement de la séquence de tir de puissance. Je répète,
Preparing to shot
lancement de la séquence
sequence.
de tir de puissance.
Preamplifier module charging. Capacitor banks at full level.
After the 4th amplification, the lasers are so strong, the scientists must avoid concentrating them on an area less than 1 square foot or risk breaking the lenses. They all converge to hit the target.
Shot completed at 11:11 a.m. I repeat, shot completed at 11:11 a.m.
Okay, A, B, C, D shots confirmed.
Here are the results.
Do they match the request?
Perfectly. We couldn't do any better. Thanks, guys. You can leave the control room.
Bullseye. The 4 lasers hit the target within 100th of a billionth of a second, in a circle 100th of a millimeter wide, the diameter of a hair. This level of precision is crucial. The slightest variation would mean failure. The team has proven its ability to master the 4 beams. When the laser megajoule is at last completed, the scientists will have to try and control 240 lasers simultaneously, unleashing 60 times more power, enough to reach fusion. The laser is an extraordinary tool for achieving fusion in the lab, offering power and versatility. But with its demand for hyper-precision and cleanliness, is it practical enough for industrial use? Maybe we need something a little more sturdy. In the American West, scientists are exploring the frontier of nuclear power, not far from Area 51. Welcome to the Mecca of American military research, Sandia Laboratories in Albuquerque, New Mexico. Here, the U.S. Army conducts micro-simulations of atomic explosions. The terrace is a nice place for coffee. In the race to achieve fusion, this is the 3rd approach. No lasers. Here, physicists try to achieve inertial fusion with electric discharges.
The facility was built to create these extreme states of matter for nuclear weapons research, but now we're doing a lot of experiments to create fusion in the laboratory. That is, a miniature star in the lab. Over the last year, we have again refurbished it, basically replacing the entire machine to increase the energy by a factor of 2. What we hope to do with this is create conditions that are even closer to what's required to create net energy gain in the laboratory. Here in the Z facility, we want to really understand how the fusion reaction works and what is required to drive the fusion reaction. The purpose of the Z machine is to create very extreme states of matter, very high temperatures, very high pressures of matter. The way we do that is store electrical energy in capacitors, discharge it on a very short time, so at the center of the machine, we deliver very high currents at very high voltage to make these very high temperatures and very high pressures. We do that ultimately to make fusion conditions in the laboratory.
During a thunderstorm, static electricity stores up in clouds until it suddenly discharges in the form of lightning. The Z machine shot works the same way, but delivers 1,000 times more energy, 20,000 times faster. The discharge represents 30 times more electricity than the whole world uses at any given moment, and lasts a fraction of a second. The Z machine funnels the energy in time and space to create a violent shock wave which compresses a fusion fuel capsule. The target is surrounded by a small cage of tungsten wires, 1/10 as thick as a human hair. When the current passes through the filaments, they instantly vaporize, forming a hollow column of plasma surrounded by a very powerful magnetic field. Squeezed by this magnetic field, the column of plasma implodes. It slams the fuel capsule at the terminal velocity of 500,000 miles per hour. The nuclei fuse, releasing a huge quantity of energy, the tiny fragment of a star to be harvested.
What I'm showing here is a demonstration of what needs to be achieved to do fusion energy with inertial fusion. This represents a compression of a factor of 30 to 1 in diameter from the size of the basketball to the size of this fusion capsule. And in doing that, you're going to increase the density by about a factor of 1,000, from solid density to 1,000 times greater than solid density. What's been demonstrated already in Z-pinch facilities is a compression ratio of 15 or 20 to 1.
Not enough to start a reaction, but the big challenge is achieving perfect compression.
In order to achieve ignition, one has to compress perfectly, symmetrically. And you can see, in fact, when I tried to do it just with my two hands here, that we have some bulges. So now we compress the capsule like a pancake. This would not work. Now we compress the capsule like an American football or an egg. This would not work. The capsule has to be compressed perfectly, symmetrically, within 1% of a perfect sphere. And this is the difficulty.
There's no computer fast enough to simulate all that's happening in these targets. And so we have to make simplifying assumptions. And not all those assumptions are right, and they can lead to errors. And so it's only by gathering data of what's really happening in the Z machine and comparing it to our simulations can we uncover the truth.
Looking inside the target at the critical moment would help refine their work. But the experiment chamber is sealed for safety. In the next building, Sandia Labs has built a giant camera named the Z beamlet laser.
It's like trying to look at the sun and see what's happening on the inside of the sun without being blinded. So we need a very bright source of X-rays, and this laser system enables us to create that burst of light to create a shadow of what's happening inside the Z machine. And so we use the laser to backlight what's happening in the inside of the Z machine.
As the shot is being prepared, the Z beamlet laser team gets ready to take a picture.
Okay, I'll sit on this side.
Attention Building 986, operations will shortly be sweeping the high bay and the target bay for a full system shot. All personnel, please evacuate both bays at this time. Thank you.
Evacuate the high bay for a system shot.
Okay, so the reason why we do sweep, there's four main reasons. One, spatial filter implosion. If in case a spatial filter lens is to crack and the vacuum is to leak, it could implode and essentially hurt somebody who's nearby. There's also the high voltage risk, which for the amplifiers, charging up to 18,000 kV for each circuit. So we want to make sure nobody's near the circuits with that.
Evacuate the high bay!
There's also the laser light risk, where there's so much light that if anybody's in there, they can unintentionally be blinded or burned or damaged in some way if they were managed to get in the beam path. So it's all for personnel safety, just to keep everybody safe and out of the way of the laser. Thank you.
Around the Z machine, the countdown has started. Nothing living or electronic could survive the electromagnetic charge that will rush into the hall. Any forgotten tool could become a dangerous projectile. The shock is equivalent to several sticks of dynamite. The high bay has been cleared. Everyone is safe inside the electrically insulated bunker, waiting for the experiment to start. The beamlet laser must synchronize perfectly with the Z machine to take the picture of the capsule during the shot.
Horsepower looks good.
ZBL?
Yes, sir.
Are you ready?
We are ready for you to arm.
Okay, gas is on. High voltage is on.
That looks good to me.
Attention building 983, Z is preparing the fire. Starting ZBL countdown, T-minus 130.
Please start the shot clock.
Charging the LTS 100 and the Marxes. Shot clock started.
All systems are functional.
How's that look?
Rod banks are charging.
T-minus 30. 50 kV.
T-minus 10.
60 kV.
Charge is complete.
T-minus 5.
75 kV. Charge complete. Arming to fire.
T0.
The shock wave can be felt across the entire base.
That looks good. Thank you, guys.
All right, let's go get our data.
The shot is a success. Though this picture doesn't look like much, it's a veritable mine of information.
We were able to capture an image of a fusion capsule as it was being bombarded by the radiation of the Z machine and being squeezed down. We were able to freeze the motion and capture an image of a capsule for the first time in the history of the Z project.
It's still slow going. The machine can fire only once a day. Obviously, not enough for a power plant.
Bill, how's it coming?
But in this hangar next to his lab, Michael Mazarakis and his team aim to improve the technology of the Z machine for commercial use. They've perfected a simple and reliable Russian invention. Like a machine gun, it can fire repeatedly, taking the Z machine a step further towards an operational power plant.
This is going to be the building block for our future inertial fusion energy power plant. It's modular too, so you can make any energy you want, any size of power plant, just by adding more components. We envision the first plant to need about 5,000 of these devices.
That would allow economies of scale in the fabrication of components for the power plant. A Russian plane on an American Air Force base? Who would have guessed? Michael Mazarakis waits impatiently for the delivery of the device to improve the Z machine. Collaboration between Russian and American scientists actually goes back to the 1960s, in the midst of the Cold War. While the American and Russian presidents were just a step away from using atomic bombs, the scientists were hoping to advance their research, and for that, they need to present the results to the scrutiny of their peers. It's not every day that a leading physicist helps unload a plane, but Michael would have carried everything to his lab himself if he had to. In the early 90s, the Z machine was almost forgotten. Suddenly, it's made a remarkable comeback.
20 years ago, we were really viewed to be the dark horse in the race for fusion. With the successes we've had with the Z-pinch implosions and the generation of X-rays, we've really gotten a lot more attention in recent years. So we now think we have a chance of really competing with the other schemes, and it should be a competitive environment where you look at multiple approaches to achieving fusion in the laboratory.
These enormous power plants have their place in the future of energy to meet the demand of cities and industries. Over time, the plants will improve in output while shrinking in size, just like computers. Teams of visionaries competing, but also devoting their lives to a common quest.
Scientists using the different schemes to achieve fusion: inertial confinement fusion with lasers, magnetic confinement fusion, and the Z-pinch. These three paths come together in a conference where people share a lot of information. So we can speak of stimulation rather than competition between the teams.
Fusion will take time, not years, but decades.
What if it didn't work? Well, in fact, I am very confident. It will work. Question is, in which time frame?
You have to be a true believer to dedicate yourself for 25 years to a project.
So I've been working on studying fusion since 1981, so almost 25 years. So I have a passion for trying to make a little star in the laboratory. And I really think we're on the path to achieving that with the Z machine.
ITER, the laser megajoule, and the Z machine. One of them will cross the finish line. Industrial reactors will follow. And a child born today should witness fusion power by 2070. Till then, today's generation has a challenge to conserve today's fuel as a bridge to the future.